Okay, hello and welcome everyone. In this video, I'm going to do a series of exercises that I have selected as relevant for review approaching exam 2 in intermediate micro. So these exercises are going to be cost curves, production function and cost curves, competition, profit maximization, cost minimization with perfect subs, perfect complements, and Cobb-Douglas production technology. And then thinking about the link between monopoly and elasticity, and then starting with a competitive market, having it become monopolized as a result of a cost-saving innovation. Anyway, so these exercises are ones that I would have been doing in class for Monday if Monday's class wasn't canceled because of coronavirus. Matter of fact, course going entirely online, so I'll have actually kind of a lot of videos like this, I imagine. We will see. Anyway, so we'll go ahead and begin. Suppose the firm has the following total cost function. Total cost is equal to 125 plus Q squared. What's the minimum price necessary for the firm to earn profit? Below what price will the firm shut down in the short run? All right, so for this one, for A, we have to find the point where the firm's going to earn zero economic profit. That's the break-even price. For this one, the shutdown price, that's the price below which the firm's going to shut down. So in the short run, that's going to be the price below average variable cost. Just have that from Econ 101. Or principles of micro. Well, the break-even point corresponds to the minimum of average cost. Shutdown point actually corresponds to the minimum of average variable cost. Turns out marginal cost crosses average cost and average variable cost from below at their respective minimums. It's just a consequence of how marginal relates to average. So that gives us two approaches actually. We could find the point where marginal cost is equal to average cost. Or you could minimize average cost using calculus, and either way you're going to get the same result. I'm going to show both of those. So suppose we start with the first one. Let's find this point. We have to solve a system of equations. We have average cost. So our total cost function is 125 plus 5q squared. Divide that by q gives us our average cost. Okay, 125 plus 5q squared divided by q is average cost. Marginal cost is just the first derivative of this with respect to q. So that's going to be 2 times 5 is 10, reduce the power by 1, so it's going to be 10q is marginal cost. And then just solving, I'm going to multiply both sides by q, so this is going to give me 125 plus 5q squared equals 10q squared. I'm going to move this 5q or subtract 5q squared from both sides. That gives me 125 is equal to 5q squared. Divide through by 5, and then I'll have 25q squared, and then solving, I have q is 5. Okay, so the other thing I could do is I could minimize average cost. So average cost is this right here. I'm going to write this as 125 plus 5q squared because initially I was like, I want to do this with product rule, not quotient rule. And then as soon as I wrote this out and I didn't want to bother erasing, I was like, wait a second, just doing the algebra actually simplifies this down to exactly what we need. So I'll go ahead and just follow through the work I'd started. So it's going to be 125 q to the minus 1 plus 5q, right? Taking the derivative, it's going to be minus 1 times 125 is minus 125 q to the minus 2 plus 5 equals 0. And then solving, again, we find q is equal to 5. And you might have taken that derivative a little bit different than I had, but you should end up with q is equal to 5. Matter of fact, both ways have to come out the same. Once you've got that quantity, we go back in and we'll exploit the fact that here average cost equals marginal cost equals the price, especially for a competitive market. So price is equal to marginal cost, which is a function of quantity. So marginal cost was 10q. So 10 times 5 gives us a price of 50. So that is going to be our answer to the question, what is the minimum price necessary for the firm to earn profit? All right, the other question we had is below what price will the firm shut down in the short run? So we have to find our shutdown price. So this was average cost. Average fixed cost is 125 divided by q. Average variable cost is 5q squared over q, which is 5q. Is average variable cost. Marginal cost is still 10q. And staring at this, we're like, wait a second, that's only going to be true after we cancel. Q is q. I should actually say this is equal to 0. So where are they equal when it is a quantity of 0, output of 0. So looking at the graphs of this thing, we see marginal cost is going to be everywhere higher than average variable cost. Matter of fact, twice the slope. So this should actually be only where q is equal to 2. Yeah, only where q is equal to 2q, which is only true when q is equal to 0. I don't know what I was doing here. S5, I don't know. Whatever. So when marginal cost is greater than average variable cost, the firm will continue to produce, at least in the short run. When marginal cost is below average variable cost, which happens everywhere for negative outputs, the firm's going to shut down. Well, that's actually not going to happen. So for all positive prices, we get a quantity that's positive produced in the short run. So going back to my comments up here, we have firm will not shut down in the short run because average variable cost is below marginal cost for all levels of output. All right. So we'll continue on to the next one. I almost forgot I had that sitting there. Marginal cost. Marginal cost. I was looking at Bob and I said marginal cost. That's how my brain works. So Bob needs to hire comedians to produce happiness and joy, or despair and sorrow, through his new comedy club. His production function for comedy is Q is equal to 4L square root of capital. He starts with capital fixed at 4. The rental rate of capital is $50 per unit. Wage depends on the amount of comedians employed. So wage is a function of labor, right? So L is like the amount of comedians hired. So that's going to be 10 plus 2L. So then the question is, does Bob's production function exhibit diminishing marginal return to labor? Well, to do this, we're going to take the production function right here, take the partial with respect to L. So the derivative here is going to be df dl, where f is a function of L and K, or just dq dl, fine, good. And so when we take this derivative, well, the 4 and the k to the half comes along for the ride. It's a constant. The L goes to 1, actually, technically. And so our marginal product of labor is just going to be the 4k to the half. However, k is fixed at 4, so this is going to be 4 times 2, or 8. Right? So it says, actually, Bob's production function has constant returns to labor. Marginal product of labor is 8. Derive Bob's short-run cost function. All right, so short run, we have a fixed level of capital. It's at 4. So now what we want to do is we want to find the use of labor, right? So Q is equal to 4L times 4 to the half, or that's going to be 2 times 4 times L, so 8L. Solving for L, we get L is equal to Q over 8, so my cost is a function of quantity. Output is going to be W as a function of labor times L plus RK. And then this is ultimately, so you're like, wait a second, this has L's and K's. Where's this as a function of Q? No, it's right over here. So what happened is W of L, we can write this as 10 plus 2L. We can replace Q over 8 here. 2 times Q over 8, that cancels, so it's going to be 10 plus Q over 4. And then rather than an L, this is going to be Q over 8, and then plus 200. So now, yes, we do have a function for costs as a function. We do have a function that gives us cost as a function of output. Or then just solving. Good. So what's the shape of Bob's marginal cost curve? Well, let's take the derivative with respect to Q. Derivative here is going to be 10/8. Derivative here is going to be 2Q over 32, or 10/8 plus Q over 16. 10/8 is the same as 20 times 16, so we get a common denominator, 20 plus Q over 16, and then this is linear in Q, so it's like upward sloping. Does the relationship W over MPL equals MC hold? Let's see. Well, MPL is 8. We saw that from above. W over MPL is going to be 10 plus 2L over 8, or 40 plus Q, or equals 40 plus Q over 32, and it ends up not holding. Why does it not hold? Well, what's going on here is this is not picking up the marginal contribution of labor to our wage, the 2L. So anyway, for a question like this, basically what I'd be asking for is you to pick up on this being weird. There's being something weird going on here with this wage, and there's a lot of things you can comment about. This is like maybe there's some fixed amount that you've got to pay, plus like increasing in the number of comedians. So you've got this like flat portion of your wage, and then you've got some portion that depends on the number of other comedians also hired, which is weird. Okay, so question 3, competition. A perfectly competitive firm has the cost function TC is equal to 1,000 plus 2Q plus 0.1 Q squared. What's the lowest price at which this firm can break even? We're trying to find the break-even price. That's the exact same exercise we did before, right? We are trying to find the minimum of average cost. And try to remind myself if I did this. I did it. Yeah, I did. So to find the minimum of average total cost, and here I am, like, this is like a major surprise to me that I did this. I wrote this out literally like a couple hours ago. So also how my mind works. 1,000 plus 2q plus 0.1 q squared over q gives us average total cost. We want to minimize this. The other thing we could do is to find it, we could just set this equal to marginal cost rather than taking that derivative. So either way that you want to solve, marginal cost is just the first derivative of this thing. So that's going to be 2 plus 0.2q. So that's where this came from. Setting those equal and then solving, that's not bad at all. We end up getting the optimal, or that we ultimately getting the output of 100. And then just price equals marginal cost. Well, let's evaluate our marginal cost at 100. So it's going to be 2 plus 0.2 times 100, or 2 plus 20, or 22, price of 22. So that's how that one worked. All right, I crossed this one out because I'm going to do this later on. And so I've moved that later. Now we'll go to profit maximization. Oh, but there's a transitional period because we did cost curves and we did perfect competition. And then we're kind of like onto a new topic, profit maximization. So it is time for puppy study break. How about that? Cool. All right, so profit maximization. Ripon Good Cookies is based in Ripon, Wisconsin. Fun fact. Actually, you drive into Ripon. This is like on this is like on their sign when you come in. Suppose the cookie factory uses 2 inputs to produce cookies according to a production function given by 2 times the square root of x1 plus x2. Cookies sell at $25 per crate. Input 1 costs $5 per unit, and input 2 costs $25. So if input 2 is fixed at 10 units, find the profit maximizing level of input 1. I believe I did write this out here. All right, so here's my profit function. P times f of x1, x2 minus omega 1, x1 minus omega 2, x2 bar. The output price was 25. My production technology was 2 square root of x1 plus 10. Minus my input price for factor 1 is 5. Input price for factor 2 was 25, fixed at 10 units. So then taking the partial with respect to x1, this drops out. And this ends up being PMP1 is equal to omega 1. Well, that just boils down to this expression here. I take this derivative. This is to the negative 1, or this is to the 1/2. So this is going to be 1/2, and then x1 to the minus 1/2. 2 and 1/2 cancel, so this is 25 x1 to the minus 1/2 equals 5. Moving this to the other side, and then dividing through by 25, multiplying through by, this is, you could think of this as 1 over the square root of x1. So when we multiply through, this comes into the numerator. So actually, this negative is incorrect. I'll put my cursor here. It looks like a positive. How about that? Problem solved. And then we'll square both sides, so we'll get 25 is equal to x1. All right. All right, what's the profit? That was the next question, is what happens to the profit level? Well, you just go back to the profit function we had here, and then we evaluate that at our optimal x1 that we just found. Put in 25 here and here, and then solve. If you do this, we end up getting what profits of 125. Not 125 factorial. I just was exclaiming that profits were high. All right. So suppose Ripon Good Cookies is free to vary its usage of all inputs. What's the profit maximizing level of factor 1? Let's see. So it's going to end up being the case that the optimal level of factor 1 is not going to change. We're just going to solve for the usage of the 2 factors independently here because of the way that x2 is entering into this profit function. Namely, we see this below, x2 enters linearly into both revenue and costs. So for part D, Ripon Good Cookies is free to vary all of its inputs. Does the firm need to change its usage of x2, factor 2, to maximize profit? Well, so we want a mathematical relationship using the output price and the factor price to characterize the effect of varying factor 2 on the firm's profits. Well, the easiest thing to do to see this is to go back up to our profit function and to say, okay, here's where factor 2 enters, here's where factor 2 enters. How is this entering in practice? Well, this is x. Did I do this down here now? I mean, this is x2 and this is x2. Every place you see a 10, that could be some other level of factor 2, but I got to change both this 10 and this 10. So if I used 11 units of factor 2, this would be 11 and that would be 11. If I use 0, this would be 0 and that would be 0. Anyway, what's happening is this 10, or this factor 2 is entering linearly, because what I'm going to do is I'm going to take this 2 and multiply it by this 25, but then I'm going to take this 10 and multiply it by negative 25. So I'm going to add and subtract 25 times whatever is factor 2 from my profit function. In this case, because 25 is my output price and 25 is my factor price of input 2, it doesn't matter, and that's why that's where we're solving for these independently, and that's why it didn't matter for part C. However, it could be different. So like, what's governing my use of factor 2? Well, suppose the output price was big relative to the price of factor 2, or suppose the output price was small relative to the price of factor 2. Now you've got something different. So if the output price was bigger than 25, bigger than the input price, then you'd use infinitely many units of factor 2. If they were equal, then you'd use any amount. And if it was less, then you'd use 0. All right. Number 5, profit maximization complements. So a competitive firm produces output according to the production function y is equal to the minimum of x and 420. Use W to denote the price of factor X and assume the price of output is $1. Find the firm's demand for factor X when the price of X is W. All right. So here's what's going to happen. This is my profit function. This is Py. Y is the amount of output. So Varian uses Y for output. And then this is Px is the amount of the input. So this is going to be the output price times the amount of output minus the input price times the amount of input. This is valid to just multiply by the amount of the output, because my production technology is going to force y equals x equals 420, right? Because that's how when you have perfect complements production technology, or perfect complements, remember we're replacing this comma with an equal sign, and this gives us the amount of, well, in this case, the amount of output has to be equal to x, has to be equal to 420, otherwise there's waste. All right, so going back to the statement here, now that I've justified why I just have y here, not like f of x z, I guess, whatever. Y minus, so this is 1. Price of the output good was just 1. So then this is the price of the input was w. If there's positive profit, this requires y is bigger than wx, right? Well, that requires 420 is bigger than w times 420, because we got these equal. And so then w has to be less than 1. And if so, then the optimal amount of input x is going to be 420. And then if not, if w is bigger than 1, then x is going to be 0. This is going to be 420 when m is less than or equal to 1, or 0 when m. 420 when w is less than or equal to 1, and 0 when w is bigger than 1. All right. Question 6. So this is to remind myself of the one that I moved from earlier. So rather than going on to this one, I got to go and find question 6. So, uh-oh. That didn't turn out the way that I was planning at all. So let's see. Let's go back to question 6. I guess it's now telling me I got to go back to where I started from. I've definitely screwed back, or scrolled back too far. So, all right, here we go. So question number 6, that was this one. Suppose, now it's all colored over. I don't know what happened to that one. So I'm thinking back, I think I deleted that page when I took out something else, so good. All right. So the firm's production function is f of lk is equal to L to the minus 1/4, k to the 3/4. I know I wrote this one out. This is so frustrating. I know I did. I know I did this one. Where did I put this? Sorry. This is driving me crazy. It's probably driving you crazy too. Sorry about that. Now it's making me dizzy. Oh, this is great. Great, great, great. Beautiful. Beautiful. All right. Oh, that's this one. What did I do? Oh, I changed my numbering system. I see what I did. All right, so now all the rest of them are all messed up. So, that's all right. So, right. I'm not gonna edit this out. I never I never edit any of my videos. I just do them all in one take. That was like the law that I set for myself. When I decided to make videos, I said, I'm not going to invest any more time than it's got to. Because people can just fast forward and delete or go ahead and go behind or whatever. So anyway. All right. I mean, the other thing is like, I'm super lazy. I'm the laziest person I know. Also super productive, which says something. But I look at the videos that I have and all the videos I've created, and I count that up, and I'm like, I've just wasted hours of my life. So that's why I don't edit my videos. All right. So suppose a firm's production function is given by f of Lk is equal to L to the fourth, K to the 3/4. Our conditional factor demands are coming from solving the cost minimization problem. What's the firm's conditional factor demands for labor and capital? All right, well, so I'm going to write out the firm's cost minimization problem. It's going to be minimizing by choosing labor and capital. So WL plus RK minus lambda, and this is my constraint. So this is the objective. The objective is to minimize cost subject to the constraint. The constraint is I want to produce Q given the limits of this production technology. All right, so take the derivative with respect to L. This right here, this DL, this is for the Lagrangian. This is like a Lagrangian L, right? So the derivative of this thing with respect to labor is W minus lambda, 1/4 L to the minus 3/4, K to the 3/4 equals 0. Right, so 1/4, bring that down, reduce the power by 1. This stuff comes along for the ride. Boom. And then the same thing for my derivative with respect to capital. Good. Solving, hopefully by now staring at this, you're like, wait a second. This is just going to, like, some things are going to cancel. First off, this is my slope of my isocost, is this W over R. Second off, those lambdas are going to cancel. Then we're going to have this K over 3L. Alternatively, like, if you don't trust that, you could solve this for lambda and then set them equal by substitution. Like, solve for lambda, then substitute for lambda, and you get a system of equations. You solve, you get this. All right, we want to compare that to the slope of my isocost. So I have K over 3L is equal to W over R. Solving, K is equal to 3W over R times L. What I'm going to do then is I'm going to substitute this down into my production technology. And at first when you're staring at this, you're like, oh, this looks awful. I'm going to have this like L to the fourth, and I'm going to have this 3/4. What am I going to do? No, because look, this is going to be, we'll distribute this 3/4 to everything. So this is going to be L to the fourth times L to the 3/4 ultimately. But that's just going to be L, right? L to the 1/4 times an L to the 3/4 is just going to be an L to the 1/4 plus 3/4. So that's just L. And then this is going to be 3WR to the 3/4. Good. And then, so labor, now to get my labor demand, I'm just going to solve for labor. That's this right here. And then I could use this expression, or I could resubstitute and solve for my capital. And it's going to be this. And there's probably ways to, I don't know, you could probably do, I don't know, that this looks almost as reduced as you'd want it to be. So what's the long run minimum cost function? Well, it's just going to be WL star plus RK star. So technically we should write this as W times this stuff plus R times this stuff. So, all right. Oh, I see what I did. I labeled 7 twice. You gotta be kidding me. Gotta be kidding me. All right, so right. Cost minimization, Cobb-Douglas. You know what we need? That's right. Puppy study break. Oh, but there's another puppy study break. Look at that. That makes me feel better. All right, so cost minimization, Cobb-Douglas. Assume a firm wants to produce Y is equal to 50 units with a production function, just standard Cobb-Douglas, x1 times x2, while factor prices are omega 1 is 2 and omega 2 is 1. Find the firm's demands for both factors. All right, so we had seen just down below that I did this one, so let's go and do it right here. So what did I do? I said, all right, staring at this thing, marginal product of factor 1, take the derivative with respect to x1, that's just going to be x2. Marginal product with respect, or marginal product of factor 2, it's just going to be the derivative with respect to x2. That's just going to be the x1. We're going to compare this to omega 1 over omega 2. Good. So that's going to be x1 over x2 over x1 equals 2 over 1. So solving, we get x2 is equal to 2 x1. And then plugging this in to my original production technology, I get x1 times 2x1, subbing for x2. So now I'll have 2x1 squared. And then we wanted to produce 50 units of outputs. So this is 50. It looks like so. Sorry about that. This is 50, right? This was 50 units. So this is 50 equals 2x1 squared. So this is going to be 25x1 squared. Or x1 is equal to 5. And then using our relationship, we know x2 is 10. Got it. And then my cost function, it's going to be 2 times 5, the factor price times the amount of the factor, plus 1 times 10. So 20. All right. Number 8, cost minimization. So Anne has the following production function: 3x1 plus 4x2, that substitutes. The price of the first factor is 2, the price of the second factor is 3. How much will it cost Anne's firm to produce 12 units of output? Well, compare the MRTS compare the slope of the isoquant, the MRTS, to the slope of the isocost. So it's going to be 3/4 compared to 2/3. Did I lose that one? No, it's this one. All right, so 3/4 versus 2/3. The isoquant is going to be steeper, right? This is 0.75, this is 0.667. All right, so if we have relatively flatter isocost, it's going to cross at our Alex solution. At the bottom here, if we're producing using all factor 1, we want 12 units. This is going to require 12 is equal to 3x1, or 4 units. It's going to require me using 4 units of factor 1, which costs 2 times 4 costs 8. Okay, hello and welcome everyone. So this is part 2 of the review, although I'll actually probably splice these 2 videos together. So anyway, so cost minimization substitutes. A firm wishes to produce 90 units as cheaply as possible using only labor and capital, with the relationship explained by the following perfect substitutes technology. So marginal product of labor is 5, marginal product of capital is 9, prevailing marginal market wage is $15 per hour, and then we have to determine the rental rate of capital. So let's see. So I had this not queued up in the right place. The question was asking us, what happens if we're optimally employing 9 workers and 5 units of capital to produce? Well, that's an interior solution. We're using positive amounts of both labor and capital for perfect substitutes. That tells us something suggestive about what the picture is going to be. Then the other 2 questions, or other 2 exercises, or portions of the exercise, B and C, is saying, well, suppose we're using some labor. What's going to be the bounds on the price that the rental rate of capital can be, such that we are using just labor? Because if capital is really cheap, we'll use capital instead. And then the analogous question is, suppose the price of capital does fall, then what happens if we, what happens to costs if we, what can we say about costs if we tip over our production plan to using capital? Well, ultimately, this question comes down to exploring what happens to the optimal solution given changes in the rental rate of capital, which is the unknown piece of information. So for perfect subs, cost minimization, we're comparing marginal rate of technical substitution to the isocost, the slope of the isoquant to the slope of the isocost. We have the marginal product of labor, marginal product of capital, wage rate. We're missing rental rate of capital. So if R is less than 27, this fraction, think of like R is 1. This fraction is bigger than 5/9. So we have steep isocosts. The smallest isocost would cross the isoquant on the vertical axis. We'd use only capital. Suppose R is bigger than 27. This would give us a situation where we have flat isocosts relative to our isoquant, and we'd use only labor. And then the one where we'd have the interior solution, that happens if we have the same slope between our isocost and isoquant, and one of our isocosts lies coincident with our isoquant, and then anything is any combination that gets us that amount of output works. All right, so in terms of the corresponding costs, well, if we are using only capital and R is less than 27, exactly using only capital, we would need, so this is corresponding to the amount of, I think I actually got these switched. This would correspond to the amount of capital we would need. So if we want 90 units of output, our marginal product of capital is 9, so we need 10 units of capital. This is actually going down here. I don't know if I don't know if this is helpful or unhelpful. We will very quickly determine. So this is going to here. And then I like how it changes it into like a real arrow. And then this is going to go to here. All right. So anyway, so if the rental, so if we're using only capital, right? It's a situation where capital is relatively cheap. We have steeper ISO costs. If we want 90 units of output and our marginal product of capital is 9, we need 10 units of capital. But if the rental rate of capital is less than 27 to make that happen in the first place, then our cost is going to be something less than 270. So I should say actually 10 times 27 is 270. The total cost is actually going to be something less than 270 because we have something smaller than 27. And then here, if we're using only labor, well, to get 90 units of output, given our marginal product of labor is 5, would require 18 units of labor. The wage is 15, so this is going to give us a cost of 270. We know that to be the case because because everything concerning this calculation is already pinned down: the 5, the amount of labor, and then the wage. And then any combination. Well, suppose we have a situation where we can use some positive amount of both labor and capital. How much is that going to cost? It's got to be 270. Can't be any less than. It can't be any more than 270. It's got to be 270 at the max. Why? Well, because if rental rate of capital was smaller than 27, you just use all capital. And if rental rate of capital is bigger than 27, you just use all labor, which you already know is going to be 270. And basically, that's all the logic for this exercise, which is actually kind of cool. You could kind of explore this exercise through what happens with the rental rate of capital, or one piece of unknown information. So anyway, I really like that exercise. All right. So cost minimization complements. An orange grower has discovered a process for producing oranges requiring 2 inputs. Production function is Q is equal to 2x1, x2. How do you solve this? Well, when you perfect complements cost minimization, you set the output equal to each of the respective groupings of input. So in other words, we're replacing this comma with an equal sign. So we'll have Q is equal to 2x1 equals x2. That's this right here. 140 is equal to 2x1. So x1 is equal to 70. x2 is equal to 140. 70 times 8 plus 140 times 3 gives us the $980. All right, so cost minimization and profit maximization. This is question 11. That's going to be that's supposed to be 11. How's it look? I don't know. I don't like that. All right, so profit maximizing firms solve. You know what I do like? Yeah, that's right, puppy study break. How about that? That puppy's gonna go chase something, I guess. I don't know. All right, so profit maximizing firms solve their profit maximization problem. Looks like this. This is the output price. This is the production technology. This is the the expenditure on the 2 factors. Suppose their production technology is 8 times square root of labor times square root of capital. Suppose this firm must use only 4 units of capital. So this is a short run problem. Faces a price list here. Find the firm's optimal input demands and total output. Find the maximum profit. Suppose they want to produce this output that we found there at lowest cost. So solve the cost minimization problem. Write down the cost function. All right, so let's do that here. So our production function becomes this: 8 times square root of labor times, 2 square root of 4, right? Factor price of labor and factor price of capital are both 1. Right, so we're going to have 8 times square root of labor times 2 minus L minus K. Take the square root here. And, oops, I didn't do that yet. So this is going to be 8 times 2 is 16. Square root of labor minus L minus K. All right, now we go to PMPL is equal to omega, because this is going to be our first order condition for a maximum for a profit maximization problem, short run. So we're going to have 1/2 from this, right? 1/2 times 16, reduce this power by 1, that's this. The derivative of this thing with respect to L is just 1, so it's this. So this is literally going to be our output price times our production technology, or our marginal product of that factor, equal to the input price. All right. I'm really tired. It is almost midnight, and I was up at 4 with that puppy study break. Puppy. All right, so let's see. So this gives us 8L to the squared, 8 times L to the minus 1/2 equals 1. So multiplying through to solve, this will be, let's move this to the other side. This is going to be 8L to the half, and then square both sides. We have 64. Good. Let's find how much output we can produce with 4 units of capital and then 64 units of labor. That's going to be 8 times square root of 64 times square root of 4. This vertical line just means let's evaluate this at these values of L and K. That's what we're doing here. So then we'll have, let's see, 8 times 8 is 64 times 2. So we have 128. Profit is going to be 1 as our factor, our output price times the amount of output minus 64 minus 4. So it's going to be 128 minus 64 is going to be 64 minus 4 is 60. Cost minimization problem, well, here's our production technology. We want 128 units of output. We have fixed capital at 4, and so we want to solve. So this is going to be divide both sides by 8. That gives me my 16, and then divide by 2. This gives me my 8, and then square both sides. That's 64. All right, and I don't know what this is doing. I don't know what that's doing. But it's not going to be there anymore. Okay, so what's this going to cost? 1 times 64 plus 1 times 4, or 68. All right. So next one, now we're moving on to monopoly. So monopoly's demand function is given by price is equal to 16/24 minus 4Q. Its total cost function is 22,000 plus 24Q plus 4 or minus 4Q squared plus 1/3 Q to the third. So we want to maximize profits. Did I do this one? I did do this one. So let's see. Here's my inverse demand. Revenue is price times quantity. I can replace price with this right here. So profit is revenue minus cost. Now I'm going to take the partial, or take the derivative with respect to output. That gives me 16/24 minus 8Q minus 24 plus 8Q minus Q squared. And then simplifying down, I get 1600 is equal to Q squared, or Q is equal to 40. Then evaluating my my market demand at a price of at a quantity of 40 gives me a price of 1464. What's my maximum revenue? Well, to maximize revenue, I want to find where marginal revenue is equal to 0. My marginal revenue is actually just this right here. So you can get to the marginal revenue from the inverse demand by either this, by writing out revenue, taking the derivative, or you could just recognize it's going to have the same vertical intercept, 16/24, and then twice the slope. So marginal revenue equal to 0. I'm going to take 16/24 minus 8Q is equal to 0. Solving, we find a quantity of 203, and then oddly enough, the associated price is also 203. At what price should the monopoly shut down? Well, the shutdown would occur whenever the price is less than average variable cost. So what we want is, we'll set price, the demand, equal to average variable cost. So we go to the total cost function, take the variable portion, divide through by output. And if you do that, let's see, where's my variable? The variable portion of total cost was this right here. Divide this by output. It'll be 24 minus 4Q plus 1/3 Q squared. That's this right here. Yep. Sure enough. And then solving, we find a quantity of 69. All right, Q squared is equal to 48. What am I doing? Why do I have to do this? I have to do this because of, oh, that is right. Really? Holy cow. No way. No way. Oh, that's why I had this approximately. Here, how about this? I look at this nice numbers, like 4800. There's no way it could be 69. All right. I hope puppy lets me get more sleep tonight. Right. When you find the associated price, it's going to be $13.48. So any price below $13.48 would cause the firm to shut down, because therefore we'd be below the price is equal to average variable cost thing. All right. So let's see. The next one was monopolist demand function is 500 minus 5q. Its total cost function is 2500 plus 100q minus 5q squared plus 1/3 q to the third. At what level of output and price will profits be maximized? Well, total profits are maximized where marginal revenue is equal to marginal cost, the corresponding output. We could find that right here. The marginal revenue is going to be 500 minus 10q. You could just take what I said before. Let's take the same vertical intercept as the inverse demand and then twice the slope. Good. Marginal cost is going to be the first derivative of this thing with respect to output. So let's see. So our total revenue, our total cost was this right here. So our marginal revenue is going to be 100 minus 10q plus q squared. Got it? And in solving, we find the quantity is 20. The associated price is then going to be 500 minus 100, or 400. So that's going to be the price and the output and price where profits maximized. There was a part B here, that's right here. At what level of output will total revenue be maximized? All right, let's find where marginal revenue is equal to 0. So that's what's necessary to maximize total revenue. So 500 minus 10q is equal to 0, or q is equal to 50. And then the associated price is 250. Alternatively, you could just find the midpoint of this demand curve. So 250 and then the 50. All right, does the monopolist operate on the elastic or inelastic portion of the market demand curve? Well, remember the market demand curve is going to be elastic above the midpoint, unit elastic at the midpoint, and then inelastic below the midpoint. This corresponds to, like if I were to draw on marginal revenue, I have to go like right through here. Hey, that's pretty good. So marginal revenue is 0 at the midpoint of the demand curve, and that's also where demand is unit elastic. So all we have to do is determine, are we producing above or below the midpoint of the demand curve? Well, let's see. We found the midpoint. It was a quantity of 50, price of 250. What was let's see, we had a quantity of 20, price of 400. Oh, yep, that's going to be further up the demand curve, closer to the origin on the output side, and then higher on the price side. So this is going to be on the elastic portion. We know that already, though. Monopolists will only always produce on the elastic portion of the demand curve. The interesting part of the exercise is this right here. I said for the purposes of this example here, we don't need to prove this, that they're only produced on the elastic portion. Here, we only need to observe that the price and quantity we found in Part B corresponded to the unit elastic portion. Part B was the unit elastic. That was the revenue portion. And Part A corresponds to a point further up the demand curve. That's exactly how I solved it. All right, so what happens to the monopolist revenue if it decreases the price and increases the output relative to the value found? Oh, well, here we're on the elastic portion of the demand curve. So if we decrease the price, since demand is elastic, we'll get a more than proportional response in the quantity side. So we'll actually operating on the elastic portion of the demand curve leads to an increase in revenue. However, we're not revenue maximizers. We are profit maximizers. All right, so monopoly and elasticity. Consider a monopolist with the constant marginal cost of $1 per unit, no fixed cost. If the price elasticity of demand is equal to -3, what price should the monopolist charge to maximize profits? Well, we have this expression, MR is equal to price times the quantity 1 minus 1 over absolute value of elasticity. This is in Varian. This is the relationship between monopoly and elasticity. We also know marginal revenue is equal to marginal cost, so I'm just going to set 1 equals this stuff, substitute in for for epsilon here, and then solving, we'll find 1 is equal to 2/3 p. Where did that come from? 1 minus 1/3, right, is 2/3 times p is equal to 1, or price is 1.5 to maximize profits. All right, and then the last one, innovation to monopolize the market. So Ripon Good Cookies, again, based in Ripon, Wisconsin, is now going to compete with Girl Scouts of Wisconsin, Southeast. This is one with my niece, I think. Anyway, so Suppose the inverse market demand for cookies is given by Q is equal to 2,500 minus 5p. Initially, both Girl Scouts and Rip and Good are producing at constant or equal constant marginal cost, C naught. Find the price they should set if they compete as Bertrand firms. Oh, they should just set whatever is this price. Bertrand pricing requires that you just set whatever is, if you have the same marginal cost, we get prices equal to marginal cost. If not, if it's something higher, you ultimately see some type of undercutting, whereas you try to price lower than the competitor. If you set a price below marginal cost, you'd be losing money. That's a bad idea. All right. Assume initially the marginal cost is 400. Now Rip and Good invest heavily in R&D, reduces unit production cost from 400 down to 350. So they can capture the market because they're the low-cost producer. What price should they set? All right. Well, to be able to solve this, what we want to do is find the monopoly solution. What the monopoly wants to produce where marginal revenue is equal to marginal cost. The marginal revenue, well, I gave you the demand. Q is equal to 2,500 minus 5p. We have to get the inverse demand. So the inverse demand is just solving the same relationship. It's the same relationship, just solving it for p. So p is equal to 500 minus 1/5 q. Same vertical intercept, twice the slope, gives me 500 minus 2/5 q is equal to 350. 350 because that's where we innovated our cost to be. And then solving, we find, quantity is going to be 375. And then the associated price is going to be 425. There's a problem though. This is the monopoly price, is 425. If you set that monopoly price and there's somebody there in the market that has costs of 400, what are they going to do? They're going to capture the market. And so in order to be able to take advantage of the fact that we've got lower costs, the highest price we can set is 425 minus some epsilon. Or sorry, not 425 minus some epsilon, 400 minus some epsilon. Whatever was our initial cost minus a little bit. We'll just barely undercut them. We'll still be a monopolist. We'll still capture the market, but we won't have true monopolist profits. Then I say, suppose they invest heavily, reduce the production cost. What's the highest cost level for Rip and Good that would allow them to earn monopoly profits? What's the highest cost level that allowed them to earn monopoly profits? So basically, I'm asking is, what's the highest cost level such that when I set that marginal cost equal to marginal revenue, it kicks out an output that's going to give me a price that's no higher than 400, actually strictly lower than 400. So this is all to say, that's this right here, competitive market is going to produce where price is equal to marginal cost is equal to 400. So I want to find the associated quantity. 500 minus 1/5 q is equal to 400. The competitive quantity is 500. So we are looking for a monopoly price of 400 minus some epsilon that's associated with the price of 500 plus some epsilon. So pretty close. We know marginal revenue. We know from the marginal revenue side already, marginal revenue is 500 minus 2/5 q. We just need to find marginal cost. So here's the monopoly's marginal revenue. The marginal cost we're looking for. So we have marginal revenue that we are going to evaluate at this quantity we have found. So it's going to be 500 minus 2/5 times 500 equals marginal cost. This gives us a marginal cost of 300. All right, so you have to really think carefully about why that works. So that's why I've got my comment here. This is all just to say we want marginal cost such that marginal revenue equals marginal cost brings us, I'm dodging my microphone, to QM, monopoly quantity, such that when we evaluate that quantity on the demand curve, it's going to be something strictly less than 400. So let's check what happens with the marginal cost at 300, right? I was asking what's the highest cost level for Rip and Good such that allow them to earn monopoly profits. Let's check. So here's the marginal cost. Set this equal to marginal revenue and solve. So this is going to be 200 equals 2/5 q, or 1,000 over 2 is equal to q. Sure enough, this is that quantity, 500, and then let's go to the demand curve, evaluating at a quantity of 500, the associated price is 400. That's exactly what we needed because we want to be just a little bit. We're found pretty close. We actually need marginal cost a little bit lower than 300 to make this work. But if we have marginal cost just a little bit lower than 300, our monopoly quantity will be just a little bit bigger, and then our monopoly price will be just a little bit smaller than 400. Anyway, so that brings us to the end here, and then let's see, puppy study break. Puppy study break. Now it's time for puppy bedtime. Thing about this picture, She is sleeping with her bottom on her food bowl and her front on her water bowl, which is empty. She's a little bit wet. And I woke her up, and she went right back to there. So, silly puppy. We do have the dog bed, but this seems to be the comfortable place, at least this time earlier. So, anyway, hope you liked the video. Hope you enjoyed the puppy study breaks. And see you later. Stay healthy.